Okay, so now we'll be considering how charges interact. As we've described previously, like charges repel, opposite charges attract. So we have the situation where positive repels, negative repels, positive attracts. And really, that's really your sort of only choices here, because as we've mentioned before, your electrostatic charges are either positive or negative. And if it's uncharged, then basically nothing happens. But if we're dealing with repulsion and attraction, what sort of things are we describing here?
Magnets.
No, not really. So magnets will come later in this topic, towards the end of this topic. But that's actually, for now, say it's a distinct separate thing for the moment. But it's similar to magnets in some ways. But in general, a repulsion or attraction is a description of a
force field.
Exactly, it's a force. So we're talking about forces, right? Attraction is like a pull, right? And repel is like a push away from each other. So we're talking about forces. And so we didn't really talk about this too much in dynamics, but ultimately this is still a force at a sort of fundamental particle level. Now, do you guys know what type of force we call this? What's the description we use?
Electric.
Close, starts with that. So
Electrostatic.
Exactly, that is the correct one. So basically we're describing here the electrostatic forces, which basically is a description of force resulting from electrostatic charges. So either it's attraction or repulsion, and that is basically going to determine your force. Now, think to what we said before. If you have a force, what type of thing is a force?
Change in accelerate. Nope. Wait.
So potentially a force could, either affect the acceleration of an object through Newton's second law. And as you do more and more of the topic, you'll, start bringing those concepts together. But right now, a very fundamental question is, what is a force?
A push or a pull.
Correct. And is it a, does just knowing the push or pull tell us everything we need to know about the force?
A vector.
It's a vector, which therefore means
you need a direction,
such as a repulsion or attraction, as well as
magnitude.
Yes, exactly. So therefore there's a magnitude involved, in other words, how strong the push or pull is, as well as the direction. Now the direction is quite simple. The direction is very simply attraction or repulsion. And depending on where your charges are, you can just work that out, right? So, if I have charge A, which is positive, and charge B, which is positive, then the direction is quite simple. You just draw the straight line between them, kind of thing. And so B is going to be heading that way. And A is going to be heading, well, that way, I suppose. It's quite simple. It's just going to be pushed away. So direction is simple, but how do you suppose we work out the magnitude?
Does it have something to do with Coulomb's?
Yes, it does. It is entirely due to Coulomb's law. So basically, Coulomb's law allows us to calculate the magnitude of the electrostatic force of attraction or repulsion, either or, depending, because all that depends on is, because we're only calculating the magnitude, the direction just depends on which way the charges go. Between two electrostatic charges. And I'll write the law in a moment, but before I do, I want you to think, what would you imagine this force depends on? I mean, if you have a force, what do you think could affect the size of this electrostatic force?
Mass.
Actually, it won't. The mass of the mass of the particle will not affect it. Actually, what did you say? It's an electrostatic force we're dealing with here. So if it's an electrostatic force, what's electrostatics all about?
Charge.
Right. So charges are going to affect it, both on the first and the second particle. All right. Do you think, just hypothetically, right? What do you expect? If the charge is bigger, do you think the force to be stronger or weaker?
Stronger.
Right. So we will find that when we write the formula. Anything else you think might affect it?
Like how far away the particle.
Exactly, the distance between them. And if you think about it, do you generally expect that, you know, the bigger the distance, do you expect the force to be bigger or smaller?
Smaller.
Right. And so basically Coulomb's law says that. It says the force, electrostatic force, is equal to K, which is, you know, a constant, times Q1 times Q2 over D squared. Okay. So what we're basically saying is Coulomb's law states that the electrostatic force of attraction or repulsion is equal to K Q1 Q2 over D squared, where F is the electrostatic force, you know, magnitude. Now, what is the unit of force? What unit do we use for force?
Newtons.
Correct. K is just Coulomb's constant, which is equivalent to 9 times 10 to the power of 9. Is that a big or a small number?
Big number.
Correct. So in general, do you expect electrostatic forces, you know, to be relatively strong or weak?
Strong.
Exactly. For you know, for the amount of charges involved, electrostatic force is actually quite strong. So it is significantly stronger. I mean, we'll do gravitational forces later in term 1 of year 12, but the electrostatic force is much stronger than the gravitational force for the equivalent sort of idea. Q1 is just the charge on particle 1. And what do we measure charge in? Nope, not ohms. That's resistance.
Oh, C, capital C.
Coulombs. And what would D be?
Distance between.
the charges, and given its distance, what would the unit be in?
Meters.
Good. So, therefore, as a very simple example, if we have, for example, a proton, if, for example, we had an electron, not to scale, obviously, and let's say that they were placed a distance of, let's say they're 1 centimeter apart, then firstly, is this going to be an attraction or repulsion?
Attraction.
This will be a force of attraction. And to calculate the magnitude of this force of attraction, it would be k times q1 times q2 over d squared. Now, I didn't tell you the charge of the proton or the electron. Having said that, you should recognize that if I told you that this was a proton and that this is an electron, questions can just tell you that they're protons and electrons, in which case you can look up your reference sheet or what we covered earlier and recognize that basically they're just your fundamental charges. They could also tell you it's a charge of, +2 or +1, and then you need to convert it into the relevant number in coulombs. So that would be 9 times 10 to the 9. Both of them are 1.602 times 10 to the power of -19. So I'll just write it as squared. Now, what would D be?
1. Oh, 0.001.
Right. Remember that it has to be in meters. So therefore, it would be 0.01. And if you go ahead and do that,
so if they tell us that like the electron has a negative, in front.
sorry, Yvonne?
So if the question tells you that the electron has a negative charge, do you just put a negative in front of it?
Well, remember, are we working out the magnitude or the direction here?
Is this magnitude?
Work out the magnitude, right? So it doesn't matter. As far as the magnitude is concerned, it really doesn't matter.
Yeah.
The positive or negative only affects, the attraction or repulsion. And we've already decided that. We've already decided it's attraction in this instance.
Okay.
It really makes no difference whatsoever. Like basically think of Q as the absolute value of the charge, if you like, if that makes it easier. Separate the magnitude of the force versus the direction of the force. And positive or negative will only affect the direction and not in any way, shape, or form the magnitude of the force. Is that clear?
Mm-hmm.
Good. All right. Now, a simple question right now would only ask you this. Now, Alicia did mention something, which is sort of, bringing in your dynamics as well. I won't probably do the calculations here. I'll just run you through the concepts. But you get the idea that therefore that means that there's this force, right? So that means there's this force on the electron and there's this force on the proton, correct? So to be clear, what's the force on the proton?
2.31 times 10 to the negative 24. Newtons.
Is that all? So it's a force, right? So you need to give
the attraction direction.
So in this case, the direction would be?
Right.
Yeah, so you would say the proton experiences a force of 2.31 times 10 to the negative 4. Number, don't forget unit, Newton, which I know you added, and then don't forget direction to the right. So that's the force on the proton. And what's the force on the electron, to be clear?
To the left.
So is it the same one?
The same number.
So what have we kind of just demonstrated? If we've got two forces, one's to the right, one's to the left, with the same number, what have we kind of demonstrated? What is this, again, validated? Newton's which law of
Third
motion? Yeah, right? This is Newton's third law of motion. You've got a force, and both of them are, again, equal in magnitude and opposite in direction. And so, of course, you know, it will may not be the focus of this topic, but you will need to do this so at some point. So the earlier you become comfortable with it, the better. But since we've just mentioned it, that means, again, that both of them will have the same forces acting on them. Now, without looking at the specific numbers, I want to ask is, what about the mass of an electron and the mass of a proton? Do they have the same mass?
No.
Which one has a higher mass?
Proton.
Right, we expect a proton to have a higher mass. Now, are the forces on both of them the same?
Yes.
They are, but the masses are different, right?
Yes.
Now, if you have a force acting on a mass, assuming no other forces here, what would you expect to happen to the particle?
Acceleration.
Yeah, all right. So you expect that these would therefore accelerate, all right? And as a result, because of the acceleration involved, you can then work out, once we're given the masses of the positive and negative charges, that they will accelerate towards each other at different rates. Does that make sense? And so we won't calculate that here, but you can look up the masses of protons and electrons, and then you could actually do the calculation, which you may need to be required, you know, by the time you reach year 12. And that's why I say you need to understand your year 11 things very well to be able to do, you know, questions in year 12. But all you need to do is, you know, take F equals ma, apply this force, apply for your F, and then once you've given your m's, which you can look up in kilograms, and then you can work out the acceleration of the electron and the acceleration of the proton. And that's it. All right. And that's Coulomb's law. Any trouble with that at all? All right. In which case then, let us continue moving on